Hello, welcome to another module in this massive open online course. So, we are looking at quadrature phase shift keying, and we have looked at several aspects. First, how to construct the modulated signal, what are the different pulse waveforms in quadrature phase shift keying, correct? What is the property that they satisfy? That is, these different waveforms are phase shifted from each other by pi by 2. Now, let us look at the detection, the processing at the receiver and the resulting performance in terms of its bit error rate. Okay. So, we want to look at quadrature. We will continue our discussion on QPSK, that is quadrature phase shift key. We want to look at the receive processing or the processing at the receiver for QPSK. And what we have seen is that for QPSK we have xt equals A1 P1t plus A2 P2t. A1 and A2, these are independent symbols, that is the whole premise of QPSK. These are independent symbols. So, what we will do is we can match filter this independently with respect to P1 and P2. So, first we will match filter with respect to H1 t equals P1 t minus tau, and also match filter with H2 t equals V2 t minus tau. Now, this will give us, now when you match filter with P1, the component with respect to P2, that is pulse P2 will go away. So, this will give us A1 times EP, where EP is the pulse energy, which is equal to 1 plus noise and tilde, and this will give us A2 times EP. So, when you match filter with respect to P2, the component with respect component along the signal space along the signal space direction P1t, that is a component along pulse P1t, will vanish, and we get A2 times EP. A2 times that is where A2 is the component along the signal space function P2 or the signal space pulse P2t, EP is 1 plus the noise N2 tilde. Okay. For instance, let us take it. So, what we are saying is that basically we match filter with respect to both. So, first, so we matched filter with respect to P1, that is the signal space basis signal P1t, alright, to make a decision with respect to A1, alright, and to make a decision with respect to the transmitted symbol A2, we matched filter with respect to P2, that is a pulse P2t, which is another orthogonal basis function for the signal space. Okay. Now, let us look at how this operates. So, matched filter with respect to, so when we matched filter, for instance, so let us say we match filter with respect to match filter with respect to Ht equals P1 t minus tau. So, what we perform is we perform convolution, that is A1. So, first of all what we have over here is basically the received signal Yt equals Xt plus Nt. This is an additive white Gaussian noise channel. This is the model for our AWGN channel, additive white Gaussian noise channel, that goes without saying. We have seen this many times before. Nt is Gaussian noise with mean 0, autocorrelation function n naught by 2 delta tau, the mean is equal to 0. Okay. Now, xt. Now let us also expand xt. Xt is a1 p1t plus a2 p2t plus nt. Now when you matched filter this with respect to ht equals p1 t minus t. So, match filter, or let us say match filter with respect to h1 t equals p1 t minus t. So, we match filter with respect to this. And what we get is basically we have yt equals xt h1t plus nt convolved with h1t. Okay. Of course, sampled at t equal to t, sampled at t equal to t. This is the signal part. We have seen this several times before. This is the noise component. Now, the signal component is given as follows. So, signal component is well a1 p1t. So, convolution a1 p1t plus a2 p2t when you convolve with h1t, that is basically integral minus infinity to infinity a1 p1 tau plus a2 p2 tau times h1 t minus tau d tau, but h1 t is p of t minus tau. So, this will be equal to a1 p1 tau plus a2 p2 tau well times p1 t plus tau minus t d tau, because note here h1 tau or h1 t, because we have to note here h1 t equals p1 t minus t. So, this implies h1 t minus h1 t minus tau equals p1 of p1 of t plus tau minus t. So, this arises basically because if you look at this, h1 of t equals p1 of t minus t implies h1 of implies which implies h1 of h1 of t minus tau equals p1 of t plus tau minus p of t plus tau minus t. Okay. So, this is p of p1 of t plus tau minus t. Now, we sample this at t equal to capital T, sample at t equal to capital T, which means I substitute t equal to capital T, and what we have is a1 p1 tau plus A2 P2 tau into, well, P1 tau d tau. And now if you look at this, I can split this into 2 minus infinity to infinity A1 P1 tau into P1 tau, that is P1 square tau d tau plus A2 minus infinity to infinity P2 tau d tau. Now, if you look at this integral minus infinity to infinity P1 square d tau, this is nothing but EP, which is equal to 1, and this you can see is the inner product of P1 P2, which is equal to 0, because P1 is orthogonal to P2, and we have seen this many times before. Since P1 tau comma P2 tau are orthogonal. So, this is equal to A1 times EP equals A1. Okay. So, basically what we have is, when we matched filter with H1, when we matched filter with H1T and sample at T equal to T. So, this is basically your matched filtering, which is basically YT with HT and sample at T equal to T. So, the signal component, that is this, we can write this as, this is nothing but, remember this is nothing but, we are denoting this part by R1 T. So, we can write this as, that is output after sampling. So, R1 T A1 plus of course NT convolved with H1T at T equal to T, which we are calling as N1 tilde, and we know after matched filtering we know A1 plus N1 tilde, and we know that from matched filtering we know that N1 tilde is Gaussian, since the input noise process is Gaussian, N1 tilde is Gaussian, mean equal to 0, and variance is N naught by 2 EP, which is equal to N naught by 2, since EP equal to 1, since the normalized pulse energy, since the pulses are unit norm, since EP equals 1. Okay. And therefore, again, now remember, A1 equals plus or minus A, where A equals square root of EB. So, A1 equals A. So, this is similar to BPSK. So, after match filtering by H1, this becomes similar to BPSK. Not saying that QPSK is similar to BPSK, but after match filtering by H1 T, which is equal to P1 capital T minus tau, capital T minus T, where capital T is the duration or the sampling instant, this the output sample R1 T is basically similar to what we have for binary phase shift keying. That is what we have on this branch after match filtering with H1 T is similar to BPSK. Okay. And therefore, the optimal detector is again the simple threshold based detector, is basically R1 T greater than or equal to 0. So, decide A1 equals 0 or A1 equals decide A1 equals, well basically A1 equals the transmitted symbol A1 equals A if R1 t greater than or equal to 0, and decide A1 equals minus A corresponding to bit 0 if R1 t less than 0. So, this is your optimal decision rule, optimal detector or optimal decision rule. Optimal detector or optimal decision rule. Okay. And therefore, now similarly for A2, correct, we have yt equals xt plus nt, where this xt is basically your A1 P1 t plus A2 P2 t. Now, this you matched filter with H2 t equals P2 t minus t, you match filter with this, and that will give you, naturally that gives you, now when you match filter with H2 which is equal to P2 which is matched to pulse P2, the component corresponding to P1 will be 0. So, this will give you A2 times EP plus N2 tilde, EP is 1 which is equal to A2 plus N2 tilde, N2 tilde is Gaussian, mean equal to 0, variance equals N naught by 2 EP, but EP is 1. Okay. So, basically if I have to represent this schematically, what we have is, we have this incoming signal, not xt, we have this yt, correct, we have yt. So, basically we can now represent this as two separate branches, one for each matched filter. Okay. So, we can have two branches, one for each matched filter. So, match filter with, so you match filter with H1 t, okay, H1 t equals P1 t minus t. This second branch you match filter with H2 t, correct, this is equal to P2 t minus t, followed by sample at t equal to t, you sample this second branch also at t equal to t, and therefore, you get here you get, well, you get R1 t, you get R2 t, and this you basically apply to a thresholding device. Okay. So, basically what this does is, if it is greater than 0, it decides plus a, less than 0 decides minus a. Okay. So, this is basically a hard thresholding operation. So, this is basically hard thresholding, this is optimal decision rule. Okay. So, this is basically for the schematic of QPSK detection. So, let me just write this appropriately. This is your schematic for QPSK okay, and these are two parallel branches, one for H1T. So, this has two branches. Unlike previous modulation schemes, like for instance amplitude shift keying or binary phase shift keying, where you are match filtering with only one match filter, here because you are transmitting two different bits on two different basis functions, orthogonal basis functions, orthonormal basis functions of the signal space in fact. So, we matched filter separately, one branch performing match filtering with respect to H1T, another branch performing match filtering with respect to H2T. So, H1T is matched to P1T, the pulse shape P1, H2T is matched to the pulse shape P2. Okay. And naturally what we get is we have, after match filtering, every channel is similar to, each channel is similar to BPSK. So, this is A1 plus N tilde, where A1 is plus or minus A, R2T equals A2 plus N tilde, where this is equal to plus or minus A, and therefore, the bit error rate will also be similar to BPSK. Bit error rate for this, bit error rate on each channel of each channel, note that this is not the overall bit error rate of each channel So, BR of channel 1 Q well A divided by sigma, A divided by sigma, or A divided by well sigma is square root of eta naught divided by 2, and remember A equals square root of EB, which is equal to Q square root of EB divided by 2EB divided by N. Okay. So, this is similar to, corresponding to a bit energy of EB, average bit energy of EB on transmitted along pulse P1, correct, and after match filtering with respect to H1 matched to P1, alright, the output on this branch, the first branch, is similar to basically binary phase shift keying. Okay, and therefore, the bit error rate will also be similar to that of binary phase shift keying, which average bit energy EB. Okay. So, this is also similar to that of BPSK. Now, similarly, BER of second channel, now if you look at this, so similarly if you look at the BER of the second channel, this is also equal to Q, well this is also equal to Q square root of 2EB over N naught. Okay. So, this is also the probability of error on the second channel. Okay. This probability of error, we can say this is the probability of error on the first channel. This is for the first channel, bit error rate of the first channel, this is the bit error rate of the second channel. Okay. Now, we come to the overall bit error rate. Now, we come to the overall bit error rate, or let us say we come to the overall symbol error rate. That is probability that the symbol is in error, probability that the QPSK symbol is in error. Now realize that the QPSK symbol, the overall QPSK symbol has 2 bits, A1 and A2. So therefore the symbol is in error if either of the bits A1 comma A2 are in error. Okay. So let us note that symbol is in error symbol is in error if either bit A1 or A2, because if even if a single bit A1 is in error, then the symbol is in error. If A2 is in error, symbol is in error. If A1 and A2 both are in error, then of course the symbol is in error. So the symbol in error corresponds to basically the union of these 3 events: A1 in error, A2 correct, A2 error, A1 correct, and A1 and A2 both in error. That is the point. Okay, and therefore if you look at this, the overall symbol error can be calculated as follows. The overall symbol error can be calculated as follows. Probability of error of first channel equals PE. Therefore, probability correct of first channel. First channel means probability that A1, that is probability that is received correctly, that is without error. This is equal to 1 minus P, because probability of error is P, probability of correct reception is 1 minus P. Similarly, probability of correct reception equals 1 minus P. Now, probability that both bits are received correctly, here we are going to use the results from probability theory. Probability bits A1 comma A2 are received correctly equals 1 minus PE into 1 minus P. This is equal to 1 minus P square, where we are using the fact that this is based on the fact that they are independent events. They are independent events, and for independent events A comma B, probability of A intersection B is probability of A times probability of B, for only for independent events. We are assuming that these two events, error events, are independent. Therefore, this is, let us say this is event A, that A1 is received correctly, and this is event B, that A2 is received correctly. So, PA equals, so we have PA equals 1 minus PE, PB equals 1 minus P. So, probability of both received correctly is PA intersection B equals 1 minus P square, and therefore probability that symbol is in error equals 1 minus the probability both are received correctly, that is 1 minus p square, which is equal to basically 2 pe minus p square, which is equal to, we know what is pe, which is equal to 2 q square root of 2 eb divided by no minus q square root of 2 eb divided by no. This is the probability of error for the probability of overall. This is important, this is the probability of overall symbol error. This is the probability of overall symbol error. So, the probability of overall symbol error is 1 minus p square, that is 2 pe minus p square, where p is q square root of 2 eb over n naught. And now you can see for high SNR, that is eb over no, q square root of 2 eb over no is much smaller than 1, that is this is significantly smaller than significantly smaller than. This implies that your q square root of 2 eb over no is significantly smaller than q, because this quantity is less than 1. So, q square of 2 eb over no is significantly smaller than q of 2 eb over q square root of 2 eb over no is significantly smaller than q of square root of 2 eb over no, which means the overall probability of error can be approximated by ignoring the square term. The overall probability of error can be approximated as 2 square root of 2 eb over no. This is the overall probability of symbol. A valid approximation for overall probability of symbol error So, this is an approximation for the overall probability of symbol error for QPSK. So, basically what we have seen in this module and in continuation of the previous modules is we have thoroughly examined this different new modulation scheme, which is QPSK, and it is very interesting because remember now we have used the concepts of signal space. So, we are using two orthonormal basis functions, that is we are using a two dimensional signal space with orthonormal basis functions p1t and p2t, and we have seen that we can transmit one bit along p1t, right, that is by using pulse p1t, and another bit independent of that along p2t, that is along the pulse p2t, and both these bits can be recovered at the receiver. First one by match filtering using the pulse filter matched to the pulse shape p1t, other filter matched to the pulse shape p2t. Alright, the decision rules on both these branches are independent. Alright, the probability of bit error on each of these branches is q square root of 2 eb over n naught, similar to that of BPSK, binary phase shift keying, and the overall probability of symbol error is 1 minus p square, which we have well approximated as twice q of square root of 2 eb over n naught, which is basically twice that of the bit error rate of BPSK. So, basically roughly this means that there are two bits, each bit can be in error, the bit error rate is roughly twice that of BPSK, although it is not exactly true because because using the results from probability theory, we know that probability of A union B is probability of A plus probability of B minus probability of A intersection B. In fact, that is what the square term represents. But since the square term is much smaller, we can neglect it at high SNR and we can simply write it as twice q of square root of 2ab over n naught. That is the overall probability of symbol error for this QPSK modulation scheme with average bit energy EB. Alright, so we will stop here and explore other schemes in the subsequent modules. Thank you very much.